Oops. Hello, guys. Hello. How are you doing? Okay, guys, today I'm very excited because we really are getting to the heart of the matter. Okay, we're going to see why we're actually working with these bloody matrices. Why are they for? Okay, really, what they're for are, and I already told you, is to help us solve a system of linear simultaneous equation. Okay, so what is a system of linear equation? It's not a big deal. You learn that in grade 10. Okay, so we've got two equations. Okay, with two variables, x and y. Why do we call them linear? Because we don't have x squared, y squared. Okay, they're not linear. It makes the whole thing way more complicated. Now, you know how to solve that, right? I mean, let's just solve it. Yeah. What are you guys? What are you into? Are you more of a substitution kind of people or elimination? I personally like elimination, especially when it's like something like this. So let's just do that. If this is your first equation, this is your second equation. You minus one from away from each other because that's going to eliminate x. Okay, so 2y minus 3y minus y is going to give us 3y equal minus 1, meaning y equal minus a third. And then I can plug that into here and say, okay, x equal 2 and a third, right? Sorry, okay, x minus a third, so it's plus a third equal 2. In other words, x equal 1 and 2/3. What is 1 and 2/3? And 1 and 2/3 is 5/3. Oh, yeah. Okay? So that hopefully is the right answer. I hope I'm not making a big mistake here. Forgive me if I do. Now, I want to show you something. Okay, so this is the system of the linear equation. Look at this. I'm going to write a matrix. Okay? I'm going to write a matrix with the coefficient of the variables. Why? Check out. Okay? So this is 1. If there's no number, that means 1, right? 2, 1, minus 1. Okay? That's just a matrix. We'll call it matrix A. Okay? That's a matrix A. I'm just writing underneath because we're going to do like the general thing. Now I'm going to multiply that matrix by another matrix, which is really a vector. A vector is a matrix which is just one column, okay, or just one row, okay. And it will be x, y. It's going to be the vector of the variables, okay. Now check out what happens if I do that. Okay, I'll get rid of this one, okay. I'm going to write down. I'm going to multiply that, okay. Matrix times another matrix, okay. So it's going to be row times column, okay. So it's going to be 1x, which is x, plus 2y, right? Okay. Over here, what's that going to be? 1 times x times 1 minus 1 will be x minus y. Can you see what you're getting? How cool is that? How flipping cool is this? You multiply a matrix by the variables, we get the equation. Almost. We're missing, right? We're missing the 1 and a 2. So all I'm going to do here is say that's equal to another vector, which is what we call the vector of solution. Okay? Obviously, if I wrote that just like that, then I'm going to say, okay, so that times that is x plus 2, and that's equal to 1, okay? Because that's one vector, right? When I multiply a 2 by 2 matrix by 2 by 1, or 1 by 2, 1 by 2 by 1, okay? What I'm getting is another 2 by 1, okay? So that times that is x plus 2, that times that is x minus y. So that's another vector, okay? Now that vector is equal to 1, 2. How amazing is this, okay? Why is it so amazing? Well, I don't know, but it is quite cool right now, okay? Because it means now I'm going to get rid of that, because this was just to show you that this bit can be written like that. That's quite cool, okay? Now, why is it cool? One thing, it's going to help us solve this system of linear equations. Secondly, we're going to be able to learn a whole bunch of stuff about this linear equation that we didn't know when it wasn't in the form of a matrix. This is what we call a matrix equation, or a form of matrix equation. So I'm going to write like a general, generally it would look like we're going to have a certain matrix A, which is the matrix of the coefficients. That's the matrix of the coefficients. Okay, these coefficients, yeah? And I'm multiplied by a vector, which is vector of the variables. Okay, in this case they were x and y. And that's going to be equal to another vector, which is some, often it's called the vector of solution. Okay, so it's important to understand that, and I'll call it, I don't know what, I'll just call it UV, okay, or AB, I'll call it UV, okay. So it's important that these three things are very different. This matrix is a 2 by 2, or as you're going to see later, it could be 3 by 3, 4 by 4, and it has just numbers, these coefficients. This vector of solution also has numbers. This is the vector of the variable. That's what we're trying to find out. Okay? So I'm going to pause here and make some space. Okay. So let's call this A. We'll say this is my, well, let's write it down like here. We're going to say that A is equal 1, 2, 1, minus 1. That's the matrix of the coefficients. Okay? Every system of linear equation has, like we call it, a representation matrix. Okay? Now, let's, for the sake of, you'll see why in a second, let's find the inverse of that matrix. Now, because it's a 2 by 2 matrix, it's very easy to find the matrix, the inverse. I don't need calculator, I don't need anything. If you remember, that's what that half method that called. All I gotta do is, okay, I gotta swap these around. I'm gonna swap these diagonal members here. So minus 1, 1. And then I gotta plug in a minus in front of the rest. Minus 1, minus 2. Okay? If I multiply these two, I should get 1. Okay? Shall we have a go and just see that? Okay? So 1, 2, 1, minus 1 times minus 1, minus 2, minus 1, 1. In fact, look, I've done it already. I just want to make sure I got it right. It does work, but I think it's worthwhile. If you've got a minute, just pause me now and see that this thing needs to be the identity matrix, right? That's the definition, okay? Matrix times its inverse must give you the identity matrix. Just pause me, try and see if it works. It does work. I had a go at it, okay? Hopefully I didn't make a mistake. Right, now, let's say, what will happen if I multiply, because this is the equation, the same rules of the equation work. Let's say I multiply the left from the left by the inverse. So I'm going to write down, okay, the same equation, but I'm going to multiply it from the left by the inverse equation, by the inverse matrix, okay? So I multiply that from the left by its inverse, okay? That is your A, and this is A minus 1. Well, if I do that on the left side of the equation, surely I've got to do it also on the right side, okay? So I must also multiply this equation, this matrix. I must multiply the vector of solution also by this matrix, right? Okay? Now, I don't need, now I need to multiply that, yeah? But I don't need to do it. You've done it. Hopefully you pause me when you've done it. I've done it before the video. And I made sure, by definition, if this is an inverse and this is the matrix, then if I multiply them, what should I get? Correct, I should get the identity matrix. Okay? Okay, now what we got to do here is, well, we need to do that. So let's do that. Okay? So I multiply this row by this column. Minus 1, minus 4, it should be minus 5, I think. Minus 1, minus 4 is minus 5. Okay. Then I multiply by that. Minus 1 plus 2 is plus 1. Okay, so I got that. All right. Oh, hang on, guys. Oh, hopefully you realize that I made a mistake. Okay. So if you pause me, you realize that I forgot something very, very serious. Okay. Luckily, I found it now, right at the end of the exercise. Okay. So this is not really the inverse matrix. Okay. The inverse matrix is that matrix, but I should have divided by the determinant of A, right? I should have divided by the determinant of A. I forgot to do it, okay? So we flip these numbers, we plug in a minus, and we divide by the determinant of A. The determinant of A is minus 1, minus 2 is minus 3, okay? So I need to time it by minus a third, okay? Need to time it by minus third. That's the inverse matrix. So now, really, if I need to have minus third here, I will get the inverse matrix. Otherwise, I'm not. Okay? So obviously, I have to do it here as well. That's not the inverse matrix. The inverse matrix is minus a third times this matrix, and therefore I also need to multiply. On the right side, I also need to multiply by minus a third. Okay? So this vector, okay, should be, hoping I'm getting the right answers here. Yes, I think I am. Okay, so I'm going to multiply minus a third by, oh, I shouldn't have erased that. Okay, let's do it again. That's minus 1, minus 4 is minus 5. Yes, I'm getting the right answer. Minus 1 plus 2 is plus 1. Okay, all right. Okay, so what happens now? Well, what I got to remember is that I've got the identity matrix. I got rid of that. And what is the identity matrix times any matrix? Okay, a vector is just another matrix. Well, it's the same vector. When I multiply identity by any vector or any matrix, it will just keep it the same. You can see it. 1, 0 times xy is x. 0, 1 times xy is y. So what I've got here is this vector of the variables, we called it, is equal to, now I'm going to absorb that minus third over there, is equal to 5 over 3 and 1 or minus 1 over 3. Okay? All right. And now I solve the problem. Okay? If this vector xy is equal to 5 thirds minus a third, that means x equal 5 over 3. Y equal minus a third. Okay? And I solved it. Okay? So why, I want you to try and understand, why did I decide to find the inverse matrix and multiply by A? Why did I want to find the inverse matrix and multiply by matrix? Because I want to find what that xy is. But in front of the xy, I had that matrix A. How do I get rid of a matrix? I time it by its inverse. If I time by its inverse, then I'm getting the identity matrix, and identity matrix times anything is that anything. Okay? Now, I think at this point, most of you are scratching their head and saying, but Mr. Lesham, what? I mean, look how long it took you. You make mistakes by calculating inverse matrix. Calculating inverse matrix is not easy, even if it's 2 by 2. I mean, we solved this, it took us 2.5 minutes. How long did this take? Okay, what's the point? Yes, but what if you have a system of 3 equations? Okay, 3 variables, x, y, and z, 3 equations. You didn't come across that in high school, okay, or you're still in high school, you call math. There's a reason, because it's very, very, very difficult. It will take a long time to solve it by substitution or by elimination. Okay, so then we can look at the matrices, because now we know that this system can be written like that. I'm going to write down the matrix of the coefficient times the vector of the variable x, y, z equal the vector of solution. The vector of solution is 6, 5, and 1. So let's write down the matrix of the coefficient. 1, you just write down the row, the first row. 1, 2, 3. 1, 2, 3. 2, 1, 1. 2, 1, 1. 3, 1, minus 2. 3, 1, minus 2. Now, at this point, we know how to inverse matrices. Okay, it's 3 by 3. It's a bit more difficult than the 2 by 2. So we can't use that method. You can find the minors, basically you can find their joint, right? Which is made out of the matrix of the minors with the cofactors and all that stuff. I won't recommend doing it. You can do what we done in the last lesson, which we are augmenting this matrix with the identity matrix, and then doing row operation until this becomes identity, and then what you have on the right side is the identity, is the inverse matrix. But really at this point, just use a calculator. If you just have a matrix just with numbers, it's going to take you less than 2 minutes in the calculator, and that's what you should be doing. Okay? So I'm just going to copy it from the table. If this is, we'll call this n. M is 1, 2, well, let's write like this. Let's say this is n. That means n minus 1, just going to copy it from the table if you don't mind, but you can obviously just use the calculator, is minus 1 over 8 times minus 3, 7, minus 1, 7, minus 11, 5, minus 1, 5, minus 3. Now, in the 2 by 2 scenario, what I've done, I multiplied that by that. But I know already what I'm going to get, right? I know that n minus, maybe let me write it like this. Let's rewrite this just in shortcut. So what do I have here? I've got matrix n times x, y, z, the vector of variables, equal vector of solutions, okay? And I'll call that u, v, w, just generally. I want to make like a general rule. Now if I multiply by n minus 1 on this side, whatever that n minus 1 is, then obviously I need to multiply this by n minus 1 as well. U, v, w. Okay? Then, what I'm getting is, because this time that is the identity matrix, and identity matrix time any vector is the same vector, so I'm going to get x, y, z, which are my variables I'm trying to solve, are basically equal to n minus 1 times u, v, w. So then I don't have to write the whole thing. All I've got to do is write this specific example, x, y, z, equal to this matrix, minus 1 over 8, minus 3, 7, minus 1, 7, minus 11, 5, minus 1, 5, minus 3, times 6, 5, and 1. Okay? In the test, that's what you guys got to do. You first of all write it down, line it up in the matrix equation style. So you're taking it from here to there. Then you use a calculator, hopefully, or any other method to find the inverse matrix. And then you just write down finally, right, x, y, z is equal to the inverse matrix times that. And then if you don't mind, I'm going to just do a shortcut here. I'm just going to see what they got. Okay, we're not going to do the whole thing. You know how to multiply matrices. Okay, what the guys are getting here is, after I multiply by minus 1, 8, is 2, minus 1, and 2. Okay, and then, you know, we're still in high school. I mean, this is actually fine. University style, you can leave it like that. But in high school, I think it's more polite just to make sure you know what that means. That means that x equal 2, y equal minus 1, and z equal 2. And that's the answer. Okay? So I'm just going to recap what we've learned. We've learned that any kind of system of linear equation, any dimension, we can work in 4 by 4 as well, can be written in the form of matrix equation. A matrix of the coefficient times the vector of variables equal vector of solution. Now, how is that going to help us find the vector of solution? How can I find the variables? What are they equal to? Well, I need to find the inverse matrix. Because if I multiply the inverse matrix on both sides of the equation, that's going to become the identity matrix. Okay, that is basically 1, or not 1, okay, identity matrix, which then I can just ignore because identity in any vector is a vector. And therefore, the variables are equal to the inverse matrix times the vector of solution. This is really what you need to remember from this whole thing. Okay? Define what the variables are equal to, find the inverse matrix, multiplied by the vector of solution. Remember, the vector of solution really are the numbers. Okay? I'm just going to pause here because there's one more thing maybe that I'd like to talk about. I'll just have to think first. Yeah, okay, so I want to just mention one more thing. There could be problems, okay? We could be problems. So far, we looked at mainly at nice, appropriate matrices. What do I mean? You know, when we calculate the inverse matrix, in all the methods really, even if we're not aware of it, we always have to calculate the determinant of the matrix. So let's say I have a matrix and I want to find the inverse. Well, the formula that we came up with was 1 divided by the determinant of the matrix times the adjoint of the matrix. Okay? In the 2 by 2, we also had to divide by the determinant of the matrix, right? What happened if the determinant of, I mean, what's the possible problem here? What's the possible problem in this formula? Okay, we didn't discuss it, but I think there was one exercise where it was the case. What happens if the determinant of the end is 0? Okay, so for example, 1, 2, 1, 2. It's the normal 2 by 2. What's the determinant of this? Okay, let's write it down. What's the determinant of this? It's 1 times 2 minus 1 times 2 is 0. So how do I do 1 divided by 0? I'm in a problem here. Okay, this is what we call the singular matrix. So we are going to have a whole lesson just dealing with that, but for this point, in case you might come across, and you have actually come across at least one question I saw where it was the case, then you have to understand that these matrices actually, the singular matrix, don't have an inverse. Not every matrix is invertible. Some matrices don't have inverse matrix. And the fact that they don't have inverse matrix, that kind of stuffs up over here. You know, that solution, if I don't have an inverse matrix, how can I find a solution? Well, it turns out these kind of matrices like this that don't have, that are not invertible, in fact, the linear system of the system of linear equations that create these matrices don't have solutions. Some equations don't have solutions, but we will have a whole lesson just about that. Right, enjoy it.